Great to see you here again. My name is Luc de Ceuster. I'm presenting you the Math Survival Guide, and in this new video I'm talking about finding roots of equations, and I will be discussing the bisection method. But before we continue, click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. Now, we try to find the roots of equations, and there are different methods. In many cases, we can have a formula that will give us the roots directly. Look at the special product formulas, look at factoring of polynomials, let's look at the quadratic function, the quadratic formula, and so on. But in certain cases, we cannot use that, and we have to use different methods. And the bisection method is one of those methods. And that's what I'm going to explain to you in this video. The first thing that we have to consider is that we try to find roots of an equation, and we use the bisection method. Now, when we look at the bisection method, we start by considering a continuous function, and we call that function f of x. Now, the fact that we have a continuous function, here the orange line is an example of f of x. It's continuous, it passes from a positive value towards a negative value. And that's very important because once we know that we have a continuous function and we know that there is an interval where the sign changes, that's also the interval where we can find the root or one root of this equation, and they can have more roots, of course, so we may have to repeat that procedure for other roots to find. x0 is the point where we have the intersection with the x-axis, so this means that f of x index 0 is equal to 0, and we find two values x1 and x2 that are in fact to the left and to the right of x0, so we find that in this case f of x1 is positive and f of x2 is negative, and we can conclude that x0 is between x1 and x2. Now basically that's what we're going to do. We're going to start here with a first interval, the interval x1, x2, in which we have to find the root x0. Now we know that from the graph that x1 and x2 include x0. So x0 is between x1 and x2. We have to find different values. We have to find the exact value of x0. And how do I do that? Well, basically what I'm going to do, I'm going to make a new estimate for x0, which is the average of x1 and x2. So basically I'm taking the two extremes of this interval. I calculate the average, which gives me a new estimate of x0, and I now have to find the next step. We have to find, when we know f x1 is larger than 0 and f of x2 is smaller than 0, what happens with x3? Where do we place x3, to the left or to the right? So first of all, let's have a look when the function applied on x3 is smaller than 0, then we know that x0 is between x1 and x3. Because x3 is closer to x0 than x2, we narrow the interval. In this case, we can say that x4 is x1 plus x3 divided by 2, or the average of x1 and x2. But we can also have a look at another case. Let's say that f of x3 is larger than 0. It means that x3 is to the left of x0. And now we can say that x0 is between x3 and x2. Now we can calculate a new average, a new estimate, which is x3 plus x2 divided by 2. And we continue with this calculation. Now it's always a question, when do we have to stop? How far do we have to continue? And all depends on the desired precision, because every time we have a new estimate, we can calculate f of x, of the new estimate, and see how close we are to 0. So when we have a higher precision, we want to have that number closer to 0. We also have to look at the number of decimals, and the number of decimals, for example, in the number 4.321, means that we have, in this case, 3 decimals. It means that we have to have a precision of 3 decimals. Now, this is a different topic. This is about significant numbers, but we have to select or to continue the calculation until we find a precision that is applicable in our solution, in our case. For example, when we look at the petrol at the petrol station, we can tank fuel up to 1 or 2 decimals, then we only will go up to 2 decimals. If we need a higher precision, we can continue with more decimals, but all depends on the problem that you're trying to solve, on the measuring equipment that you are using. Now, this means that we, let's say, we continue the calculations. In this case, if we want to have 3 decimals, 3 to 1 in this case, we continue the calculations until those 3 decimals do not change anymore. So with the next iteration, we can find 4.321 and something, but the 3 decimals that I need are not changing anymore. So that's important to decide on what you're doing, and all depends on the practical use. Now let's have an example here when we are going to a simple equation x to the square minus 3 is equal to 0. And we consider that x is a positive real number. Now we know that x to the square is equal to 3. Basically, when we look at this formula, we can say that when x is a positive real number, that x is equal to the square root of 3. And we can calculate that on our calculators, on Excel and whatever. Now, I selected this example because it's a really simple example of what we can do with this method. And we will see that we will find a result which is basically finally equal to the square root of 3. Now, perhaps you had to learn by heart at school the squares from 2 till 25, and you can in fact start this calculation from any number, but if you already have an estimation, it will reduce the steps in your calculations dramatically, and you will find the solution a lot faster. Now, let's have a look at some of those numbers. You remember 17 to the square, or 1.7 to the square, is equal to 2.89. And when we look at x equal to 1.8 to the square, we find that x to the square is 3.24. Based on this, we find that x, in this case, is between 1.7 and 1.8. And it also means that we already closed in on the interval, and the number of iterations will be dramatically reduced. Now, it's not always possible to find this, but if you don't really know where to start, you can do a quick calculation and find some reference numbers where you can, in fact, narrow the search interval. Now let's have a look at the graph, and we see how we do the first iterations. This is the x and y graph, and this is the graph x squared minus 3. And when we put there 1.7 and 1.8, we see that the values here, the f of 1.7 is negative, and the f of 1.8 is positive. Now we basically know that the value x is between 1.7 and 1.8. Now, based on this, we can calculate x1, the first iteration, which is 1.7 plus 1.8 divided by 2, which is equal to 1.75. And now we calculate f of 1.75, and we find this is equal to 0.065, which is larger than 0. So now we see that 1.75 is closer to 1.7. It's smaller than 1.8, but it's still positive. So now we know that the root is between 1.7 and 1.75. And we can go to the next step. In the next step, I start from 1.75. I know that 1.75, or the image of 1.75, is larger than 0. So I can say that x0 is now between 1.7 and 1.75. We can calculate the second iteration. We have 1.7 plus 1.75 divided by 2, which is equal to 1.725. And now we find f of 1.725, or 1.725 to the square minus 3, is 2.9756 minus 3, which gives us minus 0.0244, which is smaller than 0. This leads to the conclusion that x0 is between 1.725 and 1.75. And now we can continue with the third iteration. Again, we have x0 between 1.725 and 1.75, which gives us a new estimate, x3, which is the average of 1.725 and 1.75. And this leads to 1.7375. Again, we calculate f of x3, which is 1.7375 to the square minus 3, which gives us a positive value of 0.0189, larger than 0. So now we can say for the next iteration that x0 is between 1.725 and 1.7375. And we can do the fourth iteration and calculate x4 as the average of 1.725 and 1.7375, which gives us a value of 1.7313, and f of x4 is 1.7313 to the square minus 3 is minus 0.0026, a negative value. Now, when we look at the values, the function values of f of x3 and x4, we see that in absolute value, that number is coming closer and closer to 0. So that's very important to see that we have a convergence, that we are coming closer to the number, and perhaps the precision we have at this moment may be sufficient for our applications. But let's have a look what happens with the following steps. We continue here, and I calculated x5, and I find now that x5 is 1.7344, and f of x5 is equal to 0.081, larger than 0. Based on this, we can find x6, which is equal to 1.7329, and f of x6 is 0.0029, larger than 0. We see that this value we're coming closer and closer to 0. And when we compare this with the value of the square root of 3, we see that x approaches that value. We're coming closer to 1.7321. Now we just have to see how many decimals do we need to have, how many iterations do we have to continue, how many iterations do we still have to complete before we reach the final number. So this was an introduction into the bisection method, a very interesting method to find roots. We use this, for example, in calculations of the internal rate of return or other functions. I've seen functions like this related to the Nash equilibrium when we look at games theory. And there are a lot of applications where you have to find those roots, and the bisection method will help you with that. So basically, that's what I wanted to explain to you. We will look into different applications, different calculations, more complex formulas, and we will apply it later in some other topics. Anyway, that was it for this video. I hope you liked it. It's about calculations. It may be a little bit difficult to do them. You have to follow the presentation, the video, let's say, attentively, you also can put these things in Excel to make the calculations easier. Anyway, there are a lot of ways to use this in a practical way. But don't forget, before completing the video, don't forget to click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. Thank you very much, and bye-bye.